Hey everyone, I'm Alexandra, and I'm going to talk to you today about building private web search. So every day when we browse the web, we make search queries, and these queries often reveal sensitive information about us. This is information like where we are, what we're doing, and what we care about. And today, the way search works is that when we make a query, we send our query string over some encrypted channel to the search engine servers. And crucially, the search engine servers here learn our query string, and this is important so that they can actually compute the best answer to our query string and ship this web page's URL back to us. But unfortunately, this also means that the search engine here really accumulates a trove of sensitive data about us, and this data is an attractive target for theft in a data breach or for sale to a third party. So in this work, our goal was to build a search engine that never actually learns what its users are searching for. So in this setting, our user is going to send up only the encryption of its query string to the search engine servers, and then the search engine servers are going to perform some cryptographic protocol that will allow them to compute the encryption of the best matching web page, and then they can send this back to the user. So really here, because of the cryptographic properties of the encryption scheme, both the queries and the responses look like completely random strings of bits of some fixed length. So really, the search engine here is learning nothing in a cryptographic sense about what its users are searching for and what URLs they're retrieving. And so because of this, our search engine also cannot possibly disclose this information to any third parties. Now, there are some limitations to this threat model, the first of which is that we're not hiding when our user is making a search query or how many queries our user is making. We're also not guaranteeing the integrity of the search results returned by the search service here. And finally, we're only protecting the interaction between the user and the search engine. And so this means that the user might make some subsequent HTTP or HTTPS requests, and these could leak some information about its browsing behavior, for example, to an internet service provider. Okay, so where are we today? Well, today's large-scale web search engines learn our query strings. And again, this is because in order to answer our queries, the servers have to see our queries at some point. And so this holds even if we use a search engine that doesn't track its users, or if we interact with the search engine over Tor to anonymize our IP address. On the other hand, there exist some private search systems, so they never learn our query strings. However, these don't work at large scale. And really, part of the challenge here is that standard search techniques make many query-dependent random accesses to large indexes of data, and this is hard if you don't know what the query is. And so in particular, COAS here is the state-of-the-art system for private search, and it searches over Wikipedia, which is a much smaller corpus of roughly 5 million pages. So in this talk, I'm going to present Tiptoe, which is a private search engine. So Tiptoe meets exactly this privacy property that I described. Namely, our search engine is going to learn no information in a cryptographic sense about what its users are searching for. Our prototype of Tiptoe supports search over both text and image data, and our evaluation shows that Tiptoe can search over a public web crawl, so this is hundreds of millions of web pages here, in seconds of latency. And in particular, every query with Tiptoe is going to require roughly hundreds of core seconds of server-side compute, roughly 60 megabytes of client-to-server traffic, and roughly 0.3 gigabytes of local client-side storage. Now, the major caveat here is that Tiptoe's search results are not as good as those of Google or Bing, but we show that there's still an improvement over state-of-the-art private search. Okay, so how are we going to do this? Well, Tiptoe relies on two key design steps. The first, which is actually a standard technique used in many non-private search systems, is to turn our text search computation into a nearest neighbor search problem. And here, crucially, we're going to rely on machine learning techniques, and in particular, on semantic embedding models. And second, we introduce a new protocol that allows us to compute a private nearest neighbor search with high throughput. And so here, crucially, we're going to make use of clustering techniques that will let us first perform a coarse nearest neighbor search locally on the client, And then we're going to use an encryption scheme that's going to let us compute encrypted matrix vector products under encryption quickly. And actually, we give some new optimizations to this encryption scheme to improve its communication and its storage, and I won't have time to show them in the talk, but you can find details in the paper. So at a high level, our Tiptoe deployment consists of 3 components. First, we have a set of indexing batch jobs that takes as input some corpus of documents and then produces the data structures that we're going to need for private search. And then we have 2 client-facing services. So our user here is going to first interact with the ranking service. It's going to send up some encryption of its query, and what it's going to get back is going to be the encrypted relevance scores of some number of documents in the corpus. And so at this point, our user can determine what the best matching document is. Here that would be document 92. And so then our user can interact with the URL service to privately fetch this document's URL. And for the purposes of this talk, I'm going to focus on the ranking service because this is where all of the complexity of document ranking and selection happens. Okay, so let's rank documents. And as I mentioned, how we're going to do this is we'll start by representing documents and queries using semantic embeddings. So our Tiptoe servers start out with some public crawl of the web, which I'm representing here as just this set of images. And so what our server is going to do is it's going to take every document and map it to some point in an embedding space using an embedding model. And really, you can think of these embeddings, for example, as dense vectors of 192 floats. And the only property that we need of this embedding model is that if we have 2 documents that are close in meaning, so for example, these 2 apples here, then when we map them to the embedding space, they're going to be close in inner product distance. So really what this means is that the inner product score between embedding 1 and embedding 2 here is going to be a large value. So now what we can do is we can download the exact same embedding model locally on our client. And so for text search, this is going to require something like 270 megabytes of local storage. And so now at query time, when our user wants to search for need problem, for example, it can just run its query string through this embedding model to get some point in the exact same embedding space. And now we see that to find the best web page that answers the search query, what the user really needs to do is it needs to find the nearest neighbors of this query embedding queue. Okay, so how are we going to find these nearest neighbors, both privately and at scale? Well, we're going to start by performing a coarse nearest neighbor search locally on the client. So specifically, ahead of time, we're going to have our server group its set of documents into clusters by topic, and then publish the list of centroids of these clusters. So now our user here can download this list of cluster centroids, and again, for text search, this is going to be something like 20 megabytes of local storage. And now, when our user makes a query and builds its query embedding, our user can just use its local cache of cluster centroids to figure out which cluster is closest to its query. So here, for example, cluster 2 is the closest cluster to the user's search query. And so now what we're going to let our user do is privately search over the contents of cluster 2. So our user is going to fetch the inner product scores of its query embedding queue with all of the embeddings of documents in cluster 2. But here, really crucially, for privacy, we need to protect 2 pieces of information. Right? First, we need to protect this query embedding queue, because this leaks a ton about what the original query string was. And second, we also need to protect the identity of the cluster that we're searching over. Because again, these clusters are grouped by topic, so cluster 2 here might be the medical conditions cluster, and we really can't leak this bit of information to the servers. Okay, and so the way we're going to perform this search is using encryption. And in particular, here we need an encryption scheme that's additively homomorphic, which really just means that if we have some encrypted vector and some public, so non-encrypted matrix M, we can compute the product of M times the encrypted vector, and this is going to give us the encryption of the product of M times the vector. And it turns out standard encryption schemes satisfy this property, and in this work, we're going to use the encryption scheme from Simple PIR, which is joint work with some of my collaborators at MIT and at Google. And the reason why we're using Simple PIR here is because it lets us perform some pre-processing to make computing this matrix vector product here very fast. Namely, almost as fast as computing the same product without any encryption at all. So now what we can do is we can have our server construct some really large search index matrix. So the number of entries in this matrix is going to be the number of documents in our corpus. And our server is going to arrange this matrix so that column I contains all of the embeddings for documents in cluster I. And so now at query time, our user knows its query embedding, it knows which cluster it wants to search over, and so our user can build the vector that consists of all zeros, except it puts its query embedding at the index of the cluster it wants to search. So here our user wants to search over cluster 2, so the query embedding is at position 2 in this vector. And so now our user can encrypt this vector and send it up to the server. Now, because the vector is encrypted, the server here is learning nothing, but the server can still compute the matrix vector product between its search index matrix and the client's query vector. And the server is going to compute this and send it back to the user. And now we see that because our encryption scheme is additively homomorphic, what we're doing here is we're multiplying all of the elements in cluster 1 by 0. Then for all of the elements in cluster 2, we're multiplying them by the query embedding. And then for all of the elements in cluster 3 onwards, we're again multiplying them by 0. So really, what the user is getting back here is the encrypted inner product scores between the query and all of the documents in cluster 2. So our user can now just decrypt, find the largest entry, and conclude that in this case, the best matching document is document 3 in cluster 2. Okay, so that was a high-level overview of ranking in Tiptoe. So now let's just quickly look at Tiptoe's architecture again. So what these indexing batch jobs are going to do is they're going to read in every document in the corpus, then compute its embedding, cluster these embeddings, build the search index matrix, and pre-process the cryptographic operations on this matrix. And so then, at query time, our user can use its local embedding model and its local list of cluster centroids to interact with the ranking service and obtain the encrypted relevance scores of a number of documents exactly as we just saw. And then finally, our user is going to interact with the URL service to privately fetch URLs. And this URL service here uses many of the same techniques under the hood, but it's simpler because there's no ranking going on. So we implemented Tiptoe, and you can find our code open sourced online. And we also separately implemented our new crypto system that builds on top of simple PIR, but optimizes the communication and the storage. And finally, our prototype of Tiptoe uses off-the-shelf embedding models. So then we evaluated Tiptoe, and here we first evaluated Tiptoe's search costs compared to state-of-the-art private search. And so here in particular, I'm comparing to COIS, which is a private search system over Wikipedia. So since Tiptoe searches over a public web crawl, we're searching over roughly 70 times more documents here, and so the compute and communication numbers that I'm telling you are normalized by the number of documents. So what we see here is that Tiptoe requires this 0.3 gigabytes of client storage, and this is exactly this embedding model and list of cluster centroids. But then, given this storage, Tiptoe improves on the server compute by a factor of roughly 6,000, and on the communication by a factor of roughly 60. And roughly, we attribute these performance improvements to, first of all, Tiptoe's use of semantic embeddings, which give us concise document representations that are 2 orders of magnitude smaller than using a bag of words representation. And also Tiptoe's use of simple PIR, which has roughly an order of magnitude higher throughput than prior work. And finally, the improvement in communication here comes from Tiptoe's use of clustering, which lets the communication scale sublinearly rather than linearly with the number of documents in the corpus. So we also evaluated Tiptoe's search latency, and here I'm showing you the numbers for both text and image search over a corpus of between 300 million and 400 million documents, where we've instantiated the Tiptoe client-facing services with between 200 and 400 virtual CPUs. And what we see here is that Tiptoe's end-to-end client perceived latency is between 2.7 seconds and 3.5 seconds. So you might ask, where is this coming from? Well, the key reason why we can achieve low latency here is, first of all, because the server-side compute, which is on the order of hundreds of core seconds, is actually extremely parallelizable. So this is why we run our Tiptoe servers on a cluster of many commodity machines. And in fact, in our implementation, these servers are DRAM bandwidth bound. And second, our new cryptographic optimizations let us push more than 2/3 of the client-server communication and essentially all of the client query building cost to an offline phase that happens ahead of time, so before the user even decides on its search query, and so this is off of the latency critical path. Finally, we evaluated Tiptoe's search quality. So here I'm showing you the numbers on the standard MS-Marco document ranking benchmark comparing to a suite of non-private search algorithms. And so what this MRR at 100 score here is telling us is that Colbert, which is the best non-private neural search algorithm, ends up ranking the human-chosen result on average at position 2 or so out of 100, whereas Tiptoe, which is private, ends up ranking the human-chosen result on average at position 7.7 out of 100. And this is actually roughly comparable to the standard term frequency inverse document frequency algorithm. So finally, I wanted to conclude by showing you just a taste of Tiptoe's search results. And really, the high-level takeaway here is that Tiptoe works reasonably well on conceptual queries. Tiptoe's main limitation is that it's not as good at exact string search, and so queries for rare strings like names, phone numbers, or addresses are less likely to produce relevant results. Great, so this talk presented Tiptoe, which is a private search engine that searches over hundreds of millions of documents in seconds of latency without learning anything about what its users are searching for. And really, the two key insights that we used here are that, first of all, we can use embeddings to turn messy search computations into cheap and linear ones. And second, with recent protocols, we can actually do these linear computations over encrypted data quite quickly. So I think it's an exciting time to think about what else we can build with these types of tools. So thank you so much for your attention. You can find our code and our paper online. And I also have a demo of the Tiptoe search engine running. So you can either come talk to me afterwards, or if anyone would like to ask a search query during the Q&A period, I'd be happy to show you how this looks.
Okay, thank you.
Yes. Shubham Mishra from UC Berkeley. Really nice work. I was wondering, like, you're using like additively homomorphic encryption, right? So, if I'm not wrong, with homomorphic encryption scheme, you also need to send bootstrapping key or similar kind of keys, which is in excess of the ciphertext that you want to send for computation. So, how much is the overhead of doing that?
Yeah, so great question. We don't actually need to send these bootstrapping keys because those are generally just if you want to perform fully homomorphic encryption. So if you wanted to perform some multiplications over encrypted data as well. Whereas here we're using a search algorithm that can get away with just doing additions, so we don't need this part.
All right, thank you.
So Jan Bierbaum to you, Dresden. So first, thanks for doing something on privacy. It's highly needed. I'm wondering, for these embedded encodings for the websites, is there some way to capture like relations between websites? Because what makes the Google search great is that it can like value a website higher if it got a lot of links. So can you do something similar, or really just content?
Yeah, so that's a great question, and I think it would be a really exciting direction to extend this to improve search quality, right? So taking into account things like page rank and page importance, like, is something super intuitive to us when we click on search results, and something that we really are not using here. So it would be really nice to include.
Hi, Ming Li from SJTU. Very practical work. I'm kind of curious about if we need to add more documents into the corpus, what is the cost of Tiptoe to update?
Yes, so that's a great question. So as you add more documents, the servers are going to have to rerun these indexing batch jobs to, first of all, embed these documents, and then second of all, add them to clusters, and maybe even update the cluster centroids. But the cost here really is just proportional to the number of pages that have changed or that you're updating, and not proportional to the whole rest of the corpus size.
Okay, thank you.
Okay, so let's thank the speaker again for the great talk.
Thank you.